If you happened to attend this session last year, you may recall that I took on the persona of a certain real estate mogul who's a reality TV darling and after a couple false starts seems now to be able to stay married to a supermodel. And the reason I did that was to try to maintain control of this rather raucous session through the projection of authority. But I think the problem was I really couldn't pull off the physical similarity. Despite substantial investment in accoutrement, I couldn't get the hair right. So I thought, well, the best way to project that similarity wouldn't be to do it physically, but would be to do it in terms of character. So I thought, well, all right, how should I dress so that if that individual were here right now in Maui, Hawaii, his character would shine forth? And then it became very, very clear what to do. You dress for a colonial occupation of a tropical country. So let's hope my colonialist power surge will maintain the control that's needed to get through this last session of this conference. So let's begin right away. Our first speaker is Philip Castro. Dr. Castro received his PhD in astronomy from the University of Delaware in 2013. He presently serves as a staff scientist at Applied Optimization Incorporated. His research interests include astronomical techniques in faint object detection and characterization. The title of his presentation today is Standardized Photometric Calibrations for Panchromatic SSA Sensors. Please welcome Dr. Castro.
So my presentation is Standardized Photometric Calibrations for Panchromatic SSA Sensors. Essentially, we want to answer the question, how do you compare panchromatic satellite photometry from two different systems and compare them in an apples-to-apples manner? And I'd like to point out the co-authors who made significant contributions to this work. So I'll start with motivations, why are we doing this, move on to theoretical modeling, observations, and finish with conclusions and acknowledgements. So why are we doing this? So currently there is no standardized method for calibrating satellite photometry for panchromatic sensors across the entire SSA community. So in order to address this deficiency, we perform theoretical modeling to create a catalog of standard stars without a filter on a standard system. With this catalog, we demonstrate a process to standardize the calibration of panchromatic sensors for SSA. So this is a very high-level overview of the theoretical modeling. So first, we want to create a catalog of standard stars with spectral types. And then with that, we want to calculate the synthetic UBV-RI instrumental flux of the standard star. Then we want to calculate the measured UBV-RI instrumental flux of the standard star via the catalog magnitudes. And then we want to scale that synthetic instrumental flux to match the measured instrumental flux. And then we want to take that scaling factor and we want to normalize the spectrum of our standard star, and we want to calculate the synthetic panchromatic instrumental flux. And the last piece of that equation is to get the panchromatic 0 point, and we do that using the flux calibrated spectrum of Vega. With everything in hand, we then calculate the panchromatic magnitude for our standard star, and we repeat this for all the standard stars in our catalog. So towards this end, we have performed theoretical modeling to derive synthetic panchromatic or open magnitudes for standard stars on the Johnson-Cousins photometric system. We do this by anchoring to the UBV-RI standard star photometry from the work of Arlo U. Landau or Landau 2009. We cross-correlate the standard stars from Landau 2009 to the spectral types from Pickles-DePagny 2010. We clean for only robust standard stars, and this leaves us with a catalog of 289 standard stars that have UBV-RI photometry and a spectral type. And it's these two ingredients we need for the modeling. So the curve here on the left is the quantum efficiency curve from Landau 1992, and the curves on the right are the UBVRI transmission curves. And it's these that define the spectral characteristics of the Johnson-Cousins photometric system. And it's these that we use to model his system. So this plot over here shows how we actually calculate the synthetic photometry. So this example is for SA109-537, AG25 spectrum. And we'll be using that standard star throughout the presentation. So here the black solid line is the spectrum. The dashed colored curves are the UBVRI transmission curves we just saw. And then at the bottom, the gray solid line is the quantum efficiency. So using the R band as an example, first we take the spectrum and we convolve it with the R band transmission curve. That gives us the dotted red line just below the dashed red line. We then take that convolution and we convolve it with the quantum efficiency of the gray solid curve. And that yields the solid red curve at the bottom, and that is our synthetic instrumental flux density. We then integrate that to get our synthetic instrumental flux for the R band, and then we repeat that for the other bands. This gives us the synthetic instrumental flux for UBVRI. Now, two important things to note. The instrumental flux for UBVRI is arbitrarily scaled since our spectrum is arbitrarily scaled. It's normalized. However, the relative instrumental flux between UBVRI is not arbitrary. OK, so now that we have synthetic instrumental fluxes, we want to eventually scale them to measured instrumental fluxes to put them on Landau's instrumental system. So to do this, we need to get measured instrumental flux. So the first step is to get the 0 point for UBVRI, and we get that via the flux calibrated spectrum of Vega. And we have the UBVRI photometry from Landau 2009 of our standard star. Again, our example is SA109-537. And via Pogson's equation, we solve for F1 the instrumental flux as measured by Landau. And that's shown here. OK, and now that we have the measured, we can scale the synthetic instrumental UBVRI flux to match the measured instrumental UBVRI flux. And we do this via a chi-squared like best fit. And this puts our synthetic instrumental flux onto Landau's instrumental system. And that's shown here. The circled are the measured bands. The squares are the synthetic bands. And you can see you get a pretty good fit for BVRI. There's a discrepancy in the U band. I won't go into that because that's a detail in the paper. And for that reason, we use BVRI to do our chi-squared like best fit. Now that we have our scaling factor, we can apply the scaling factor to our arbitrarily scaled spectrum. And then we can convolve it with Landau's quantum efficiency, integrate, and you get your synthetic instrumental flux in the open. We repeat this process for the flux calibrated spectrum of Vega, convolve it with the quantum efficiency, and integrate, and you get the synthetic instrumental flux in the open for Vega, your calibration star. Again, using Pogson's equation. We have everything, and we solve for M1. That gives us the synthetic open magnitude on the Johnson-Cousins photometric system for our standard star. We repeat this process for each of the standard stars in our standard star catalog, and this yields 289 standard stars with open magnitudes on the Johnson-Cousins photometric system. OK, so like any good scientific process, anytime you have a theory, you also have to test that theory and verify it. So towards that end, we've performed observations with two goals. The first is assess our derived synthetic open magnitudes, and the second is to demonstrate the calibration of panchromatic satellite photometry. Towards this end, we performed observations from 2 different sites using 3 different telescopes on the same night. The first site is located in Dayton, Ohio. It has 2 systems, the Quad and SRO. Second site is in central Utah, and that system is called Rover. And I'll make note that the latitude of these is extraordinarily close, and so the longitude is the geographic difference. We had 3 satellite targets, Galaxy 19, 25, and 28. We get the average B minus V color index from the AFRL Geo Color Photometry Catalog, or the GCPC. However, we could not get that for Galaxy 19 due to insufficient data. We also observed 4 standard stars from SA109 and a 5th Vega-like calibration star, SA114-750. So the figure on the left shows the quantum efficiency curves for Landau, is the gray solid curve. Blue dashed is quad. Red curve is SRO. Green curve is rover. And it's the difference in the spectral response of these systems compared to Landau's that gives rise to a color term. And the color term is important because if you want to calibrate your photometry from a measured system, you need one, the 0 point that puts you most of the way onto that standard system. However, you need the color term to put you completely on that system. And the color term is over here, your color term coefficient times the color index of your target. So you need a color index of your target to get your color term. And you can calculate your color term coefficient as shown here, the example for rover, B minus V on the x-axis, M catalog minus exoatmospheric, M instrumental on the y, and the slope of the curve gives you your color term coefficient. We get a color term coefficient of quad near 0, for SRO a little bit redder, 0.06, and for rover significantly redder, 0.27. And it's not too difficult to see how that could be the case if you compare the blue curve quad to the gray curve of Landau's quantum efficiency. In this region, it collects less flux. In this region, it collects more. In this region, it collects less flux, and in this region, more. And it's not too difficult to imagine that the net result of that could yield a color term coefficient of 0. And if you look at the red curve, it's slightly redder than the blue curve, and you get a slightly redder color term coefficient. And then the green curve rover is significantly redder, and you get a significantly redder color term coefficient. So this shows our satellite signatures for Galaxy 19, range normalized exoatmospheric. So the red squares are SRO, the blue circles are quad, and we can see these are comparable, and they are within their error bars, which are not shown here. However, the green triangles of rover is significantly offset from the other two signatures. So one important thing to note here is that while we're observing with panchromatic systems, we do not know the simultaneous color index of our target. And it's for this reason that we can't calculate our color term, and therefore we do not take that into account. And I'll note that the Galaxy 25 and Galaxy 28 signatures are analogous to this behavior shown here, where there is an offset between rover and the other two signatures. So for two systems at the same site, the offset is attributed purely to color term, and this is because we've taken out all other possible variables. And the signatures shown here are consistent with that. But for the offset between different sites, we attribute the offset to color term and viewing angle differences. And when we say viewing angle differences, we mean Ohio will see a more easterly portion of the satellite, while central Utah will see a more westerly portion of the satellite. So although we don't know the simultaneous B minus V color index, we can make some rough estimates and approximations. We can take the average B minus V color index for Galaxy 25 and Galaxy 28, and we can use that to estimate the average contribution from the color term. And by no means am I saying that the color term or the B minus V color index of the target is indeed constant. It will vary throughout the night, especially glints, and the offset itself varies. But we can get a rough order of estimate, a rule of thumb, and we can use that color index, calculate the color term, and see the contribution to the total offset. And that turns out to be 2/3 of the average offset is due to color term, and 1/3 is due to viewing angle differences. So the conclusions from this are that color term cannot be ignored in calibrating panchromatic satellite photometry. And then if some way you were able to place the satellite photometry firmly on the Johnson-Cousins photometric system, that is, if somehow you had simultaneous B minus V index of the satellite throughout the night, and then you could apply the color term for the satellite, still viewing angle effects that are real and correct from the perspective of each observer may result in differences between your satellite photometry. And last, we need to verify our synthetic open magnitudes, and we do this by observing SA-114-750, a Vega-like calibration star. We already have our instrumental flux values from our calibrations. And again, via Pogson's equation, we have everything, and we calculate for M1 the empirical magnitude in the open. We need to apply a color term to these because they're not yet completely in the Johnson-Cousins system. We apply the color term, and we can then compare to our derived synthetic open magnitudes, and here are the differences. The important thing to note is the green ellipse. This gives the average of the absolute value of the differences for each system. And from this, we can conclude that the differences for each system are on average a few percent to 5% on the order of the uncertainty and the empirical magnitude. And based on this, we conclude that this provides evidence that our synthetic open magnitudes are indeed on the Johnson-Cousins photometric system. So in conclusion, we derived synthetic open magnitudes on the Johnson-Cousins photometric system for 289 standard stars. This catalog is available for use by the community in order to calibrate their panchromatic sensors. And then I'll skip to the bottom to save time. The color term coefficient for panchromatic systems needs to be characterized so that the size of the satellite color term can be estimated in order to determine what inaccuracies may exist when comparing panchromatic satellite photometry between two systems. Acknowledgements and questions, discussion.
Questions for Dr. Castro? Okay, I'll throw one out. We hear talk a lot about 1% photometry. We're going to get 1% photometry. We're getting close here. What more needs to be done with this technique to make that possible?
The higher accuracy you want, a lot more has to go into it. You want to calculate.
Do we need more stars that are calibrated this way so the field contains more, or?
Color term is definitely beyond the 1%. But there's some uncertainty in our color term coefficient to begin with. You could do an entire night of calibrations that would knock down that noise. But you definitely need to refine whatever it is that you're going to do. It would be color term for the panchromatic. You have to take into account color term. And then even still, if you do, there are viewing angle differences that for the one was 0.1 magnitude. So even if you get the 0.01, how do you know what differences you're going to get from viewing angle?
Right, because it's not homogeneous. Good. So, any other questions? Thank you very much. Our next speaker is John Lambert. Dr. Lambert received his PhD in astronomy from New Mexico State University in 1985. After a nearly 50-year career in SSA sensor development and data exploitation, he presently serves as a senior consultant for Cornerstone Defense. His research interests include sensor development and algorithms and techniques for satellite detection, tracking, orbit determination, and characterization. The title of his presentation today is Open Filter Optical SSA Analysis Considerations. Please welcome Dr. Lambert.
Good afternoon. The talk I'll be giving is somewhat related to the previous talk you'll see as we go along. I'll start off with a historical overview of how we got to where we are on open filter observations. Optical observations of satellites began with the launch of Sputnik in '57, and that led to much more detailed observations for characterization, especially in the mid-'60s. There were multiple agencies and observatories that got involved in the process. Not only was AMOS established in 1966, 50 years ago, but several other observatories for characterization came online in the same year, including Air Force sites at Malabar and Sulphur Grove, just outside of Dayton, Ohio, and another site at Cloudcroft, New Mexico. And there was also a NASA facility, a portable facility, one of the earliest that came online that same year, that did some very interesting work. Early measurement types included the whole range of astronomical techniques trying to understand characteristics of satellites. Photometry, open filter, just using the broadband response of your detector, multicolor photometry using the Johnson filter system. There's an example of one of the earliest measurements. Spectrophotometry using higher resolution spectral measurements of satellites to see the actual structure of the reflectance spectrum. polarimetry, looking at the reflection characteristics on polarization, infrared radiometry, imagery, of course, and laser illumination. Laser illumination was very prominent in those early days before restrictions were put in place. Optical observing techniques, the earliest observations just after the launch of Sputnik were in the optical regime, but mainly for tracking information, using theodolites or Baker-Nunn cameras to get the trajectory. The real characterization efforts began using photomultiplier tubes, which were just a point source. You would image the target on your detector, track it across the sky. There were open filter measurements, color measurements. Calibration was done using all sky techniques, where you would move from star to star across the sky, watching variations with elevation angles to get extinction or absorption by the atmosphere, as well as brightness calibration. The Landau fields were a definite benefit to doing this all-sky calibration. There were clusters of stars you could use instead of trying to memorize each star in the sky. A lot of the mount pointing at these times was done manually, so you would actually steer from one star to another. I got to know the G-type stars in the sky very well. Later transition to wide field television and CCD sensors. That includes geodes and current space-based SBSS, where you would image an area of the sky, see the stars, and see the satellite moving through the stars. And the calibration technique here was in-frame calibration, where you would use the stars in your field of view to calibrate the object. So you would get a sample of the background and sky for ground-based systems where you were looking at the particular satellite. Some of the earliest photometric analyses included the standard filters, like I mentioned. You had to do color transformations between your particular system, because nobody ever matches the standard system exactly. That includes not only your detector response, but also your optical system as well. The mirrors and lenses will affect your color transmission. The early focus in this initial work, the real need we had was to determine the configuration and motion of the satellites. That was primary interest at the time, that imaging techniques had not evolved to that point where you could photograph a low altitude satellite and see what it looked like. And motions, a lot of satellites were unstable, or you wanted to take out the motion so you could see what the thing really looked like. That type of data was used for detecting fainter objects, and also for conflict resolution and change detection. That if you saw a satellite that was stable one day and unstable the next, you would want to change your indication on the satellite catalog. Secondary importance at that time was the more detailed characterization, where you would look at the spectra of the object, try to determine what it was made out of, was it painted, or what type of materials were on the outside. Polarization gave you information on the surface materials as well. Things have changed over the last several years. The increase in the capabilities of systems, radar systems, ground-based imaging systems have taken over a lot of the work on low-altitude satellites. We can now get very, very good imaging. We can do a lot of motion or imaging with the radar sensors. But at the same time, those sensors were becoming more capable. The area of interest for optical systems and optical characterization was moving to deeper space, especially GEO. The increase in population at GEO and the benefits of optical systems using the sun rather than ground-based illumination like a radar, gave you a big advantage at much longer ranges. There are some other benefits as well, that the target illumination changes much more slowly on a deep space satellite. So you have more time not only to make broadband measurements, but also to do filters and that you just didn't have time. The time scales in deep space are on the order of hours for a measurement versus minutes for a low altitude satellite pass. And it gives you more time also to multiplex between multiple targets. Here's an example of a long signature on a deep space satellite. This is a geo satellite that we stayed on for the entire night. So you can see you have hours of availability of the target. Okay, and the photometric observing improvements at this time to the present were documented 2 years ago, a paper by Payne and et al. Okay, current SSA observing priorities vary based on the application. Surveillance, where you're trying to do metric measurements, orbit determination on a satellite, normally uses open filter photometry. You are trying for primarily detection of faint objects and metric accuracy. The SOI, space object identification, is a secondary priority where you're trying to get information on the shape and dynamics, and it's used primarily for conflict resolution. You see two nearby objects, you look at them. If one has been historically brighter than the other, you use that as part of your tagging of which object is which. And status change, like I mentioned, tumbling one night, stable the next. You monitor the activity of the satellite. These are light-starved applications where you want the maximum sensitivity for detection, and you want good signal to noise to do the stability analysis and brightness. But that's a secondary application. Examples of systems doing that are GEODS and SPSS. They're primarily surveillance systems. Want to cover as much of the space volume as possible in the shortest possible time, do frequent revisits of satellites with an emphasis on orbit determination. The space object identification, or SOI, requirements are different. Here you want to be able to characterize the object. You're willing to give up some detection sensitivity in order to get enough light to do the more detailed measurements. You're relying a lot on photometric accuracy to be able to determine size, and you want to ensure that you're compatible on these brightness measurements between different sites. So you're more interested in detailed photometric calibrations. So those lead to much more detailed characterization of a target, typing of a target, and object classification. And I've thrown in a third mission area, orbital debris characterization. It's got its own priorities. Not only do you want to detect very faint objects and get good orbit determinations on them as much as you can, but you're also interested in physical characterization. You want to get reasonably accurate brightness measurements so you can do sizing on these objects and determine other characteristics. So the requirements for orbital debris are more balanced between the different criteria than the other two types. Okay, open filter surveillance has its own challenges. Here's an example of what an open field image looks like. This is actually a ground-based image of a satellite I chose, but you see the satellite moving against the star background. I chose this particular image because it happens to be my satellite, SPSS, space-based space surveillance satellite. I just happened to stumble across it, but you can see what the field looks like. You've got a lot of stars you can potentially use for calibration. And you can get astrometric positions by comparing the position of the satellite to the stars, as well as photometric information along the streak of the satellite. You identify the target, and you extract the star images and extract the information. The reference star criteria you use depends on the magnitude of the star. You want to get for astrometrics, you want to get a good signal to noise, so you can do centroiding and get the star positions very accurately. And for the photometric part, one of the requirements in the past has been that you choose a very narrow range of spectral types so that the color response of your system is consistent. And in the past, we've always chosen G-type stars if for no other reason than that they match the illumination source. But one of the challenges is that you don't know the color of the satellite, and that makes accurate photometry on the satellite extremely difficult in an open filter passband. There are different criteria for star selection depending on your system, and in open, in-field calibration, where the satellite happens to be in the sky, you have the challenge that the distribution of stars, both the density and spectral types, may be limited, so you don't have that much of a choice in what stars you use for the photometric reference. And so you go in, you pick out some good candidates, but to get enough stars, depending on your calibration system, you may wind up with a range of spectral types, which in an open filter response will lead to scatter in your calibration results. Okay, and the impact of the color of the satellite is really significant here. Here are two examples of satellite spectra taken at fairly high resolutions. The first curve shows the spectra of two white painted rocket bodies. The blue dashed line is a laboratory sample of a paint. The red and green lines represent the observed spectra. The big significance here is that it's fairly uniform across most of the visible wavelengths, but then you get this sharp drop in the blue, around 4,000 angstroms. Okay, on the other side is a spectra of a different satellite. This is a reflection off of a solar panel on a geosynchronous satellite. And you can see that there's a very strong increase in the blue as you approach 4,000 angstroms. But the mid wavelengths, the mid color wavelengths, are much flatter, much lower responsivity. So they're almost the inverse of one another. Making an open filter measurement of these two satellites and trying to compare it to a G-type star puts in a lot of uncertainty in your measurement and corresponding uncertainty in what the brightness of this satellite is. Okay, satellite spectra are also not known to start off, but here's an example from Payne et al.'s paper from 14 that shows that the color of the satellite also changes during the night. So even if you have an idea of the materials, the color changes. Okay, so move along. Suggestions to improve the filter photometry would be, one, to get sites to document how they do their photometric calibrations and what they use. Normally, most of the references to observing sites say they measure the V-band magnitude of a satellite. I don't believe anybody doing open filter photometry measures the V-band magnitude. What they do is measure several stars, use their V-band magnitude, and get a corresponding signal. But depending on the spectral type of the star, the broadband flux may be much higher or much lower than, say, the V-band or the total flux from a a G-type star with the same magnitude. So one of the possible techniques is to use a filter system that is broader band and has calibration sources. Or one technique I've been looking at is there are algorithms for calculating the black body temperature, the temperature of a star based on various spectral systems. Here's an equation for the Johnson filter system. You can get a temperature for the star, approximate its spectral distribution as a black body, and use that total flux as your reference in your broadband system. Open filter systems have limitations, and at this point, the best you can hope for doing open filter calibrations with stars is to be consistent in your measurement system. And applying that to satellites, if you've got good determination of brightness against the stars, you can do relative comparisons against satellites. And one of the side benefits of this is that if the noise in your calibration is low enough, if you're trying to determine albedo, for example, for debris objects, reflectivity, you may start to see clustering of the albedo as a function of the radar diameter, if you're using it as the size, and be able to relate that to material type of the satellite. Okay, thank you.
Thanks very much, John. We'll have to defer questions this time till afterward, but it looks like some fine wine is coming of this idea in what was presented in the presentation before yours. So okay. You were proleptic in guessing at what could come next. So let's move to our next speaker, which is Tamara Payne. Dr. Payne received her PhD in astronomy from New Mexico State University in 1993. She presently serves as a principal scientist for Applied Optimization, Incorporated. Her research interests include sensor calibration, modeling, and analysis of photometry, spectroscopy, and imaging. The title of her presentation today is A Discrimination Analysis of Sloan and Johnson Photometric Systems for Non-Resolved Object Characterization. Please welcome Dr. Payne.
Thank you. It's nice to be here again in Maui and close up the conference with some exciting work that we're doing with trying to make filter photometry a little bit more operationally feasible. So I'd like to recognize my co-authors. Let me find my deal. Here it is. Philip, who you've already met, Jay Moody, who is here, and the Sensors Directorate and the NASIC. First, I'd like to talk a little bit about why we did this study, what we did, how to approach this work, what the results were, and our conclusions. So our main motivation is that we would like to have accurate photometric calibrations, but without having to take the time off of target, off of satellites for those calibrations. Typically, either people who are doing in-frame photometric calibrations are either using techniques or star catalogs that have low photometric accuracy, or they're using all-sky calibration techniques, which take time away from your ability to spend on satellites. With the upcoming anticipated Pan-STARRS catalog, which will have millions of stars in it all over the sky, we would like to try to take advantage of some of those modern catalogs. Unfortunately, or fortunately, they are all in the Sloan photometric system, and all of the work previously using filter photometry and characterizing satellites by their color signatures has been done in Johnson. So our real question that we're trying to answer today is whether or not we can use the Sloan filter set and take benefit from the better photometric calibration catalogs and still maintain a high discrimination and characterization capability for satellites. So our approach was an empirical one for a variety of reasons that I don't have the time or the fortitude to get into. So we used Jay's system, Agilimetrics rover telescope, which you saw a little bit in Philip's presentation, and we chose 4 satellites that are representative of several different bus types and were launched at a fairly large range in ages. The observations were made in a night in May. You can see the exposure times that were used for these satellites. We go to a satellite, cycle through the filters, and then go to the next satellite, etc. That ended up with about 33 revisits for each satellite. And then these are the stars. We used an all-sky calibration technique on these stars. And we take more than one frame in order to help calculate our measurement uncertainties. These are pictures of the different satellites on the right. These are the photometric systems in question. I want to say we're big fans of Dr. Don Goldman, who is otherwise known as Astro Don. And he has taken the Johnson-Cousins system and made a set of filters that are really fantastic in their higher transmission, where you lose very little sensitivity from putting the filter into your optical train. And then the Sloan systems also have a really high transmission. So one of the things that I want to point out is we're not using the U filters for a variety of reasons, mostly that the CCDs that we use in the SSA community are usually have very little sensitivity in that wavelength regime. And, oops, wrong button. Hello. I wanted to note that the main concern that, one of the main concerns we had with the Sloan filter set is that the G filter cuts on at about 400, whereas the B filter in the Johnson cuts on at about 350. And as you saw with John's talk, there's a spectral feature from the solar panels that is pretty strong in just those little 50 angstroms. And we use that feature very often for characterizing satellites. So it's a very discriminating feature, and we don't want to lose that capability. So the data reduction was done in the typical way, but I just wanted to show this chart to say that here are extinction coefficients for the site in Utah with their errors, and the 0 points magnitudes for each of the filters here, with a total error being calculated, with the square of that error being the sum of the squares of the other, the contributing. So our results are going to be shown. First, I want to show you brightness signatures of the 4 different satellites in the different filter systems. Then we're going to go and talk about color signatures for each of the satellites. And then we'll finish up with the analysis of the discrimination capability. So the first satellite here, I want to point out that this is, for all these charts, this is going to be the Johnson filter set. This is going to be the Sloan filter set. We're going to, we plot signatures as a function of the phase angle. So over here, this is the western side of the satellite being illuminated all the way through midnight, and then into the, where you're looking at it face on, or fully illuminated. And then over here, you're looking at the eastern side of the satellite illuminated as the sun begins to rise. This is magnitude on this side, calibrated magnitude, exoatmospheric and range normalized. and we have brighter up at the top. As you can see, each one of these the brightness in each one of the filters follows basically the same path, although there are differences in the slopes, and that's what gives rise to the color features of the satellite. You can see that both photometric systems behave similarly, and that the B, or the bluer part of the signature, the bluer brightness is fainter than the redder brightness. That's also true for NMIC 6, but you see that it's got a much different behavior. There's no hump around this phase angle. SES2 is a very interesting signature, and I want to take the time to say it's got similar behavior as the other two satellites, except in the Sloan filters, where the Z band is actually a little fainter than the I band, which is not what we have seen so far. We went back to check and make sure that we didn't make any mistakes with that, and that appears to be a real effect. So that's a first indication that the two photometric systems might be behaving a little bit differently. The other thing I want to point out is you might have noticed these gaps in the data. These are when we go off and look at the stars. And you can see that satellites behave much like children. When we are looking at them and observing them, they seem to behave properly. But as soon as we turn our back, something interesting happens. And so in this gap right here, this thing was glinting while we were looking away, and we just caught the very edge of it. And we like those glints. They're very indicative of what's going on with the satellites and are used in our fingerprinting process. Spaceway 3 is by far the liveliest of the signatures, where there's a lot of glinting right in here. Again, the gaps really hurt us in trying to understand this. It has a secondary glint, not a very slow, big shoulder like those other satellites, so you can kind of see where the differences are. Okay, so now we're going to form some colors, and let me just go over the combinatorics of all of this. If you have 4 filters, then you have the ability to make 6 different colors or filter combinations. A color is defined as the magnitude in one filter minus the magnitude in the other. And as you may recall back from Philip's talk, the differences in magnitudes are actually ratios of the fluxes. And so the ratio of the blue to the red or the blue to the green gives you an indication of what you would see in color. So for both systems, we have 6 combinations. That means if I want to create a color pair, I have 3 choices in each system that are non-degenerate. Skipping over a lot of analysis, I want to show you that these are the results that we're going to show you here today. And we're going to focus on these combinations because we've seen that they give us a little bit better separation and discrimination capability. And for all the data, you can see the paper. So here is an example of the color index signatures in the Johnson-Cousin system for the 2 colors that we care about, or 2 color pairs we care about, B minus R and V minus I. And each plot has all 4 of the satellites on it now, and there's some statistics there about the color. And I want you to note that this is, again, the same same x-axis, different y-axis, where the lower the color index number, the redder the object, the bluer the object is. The larger the number, the redder the object is. And so you can see that over the course of the night, these satellites tend to change color. I wanted to note that Spaceway 3 has a very significant glint of 0.2 magnitudes in this Johnson-Cousin system. We saw that in the previous photometric signatures. And in Sloan, similar behavior. And we also get a blue glint. So that's an indication to me, very suggestive that we still might be getting very good discrimination capability there. Not all glints go blue, and there's a really great poster paper by our Australian friends. I hope I say the name right, Jolly or Jolie. That paper shows he studied these glints, and he's got some very interesting results on them. Another paper by a cadet at the Air Force Academy, Whites, also did a paper which on spectroscopy and shows some spectra of some glints. So please, if you have time this afternoon, check out those papers. So now we're going to get into what does all this really telling us. So a very good way of looking at all this information all at once is a color diagram. And on the x-axis, we've got our redder pair, B-R and G-I for Sloan. And on the y-axis, we have V-I and R-Z. And you can see just by eye how similar they both look, which is a good indication that we're still getting good discrimination and we're not losing anything from one filter set to the other. And so in general, qualitatively, we can see that we have similar behavior in both systems. We still get NMIC 6 and spaceway 3. Unfortunately, they're clumped together. We get this little blue tail in both of them. So neither one of them distinguish between the two very well, but we're not losing anything. In Sloan, we appear to have gained a little bit of separation versus Johnson. Here, the separation in this axis seems to be about the same between the two systems. And finally, we get this distribution here. So, but we can do better than this, than qualitative. And so we want to do a quantitative measurement of how well we're doing. And in order to do that, we use the Mahalanobis distance. And we form cumulative distribution functions for each one of the satellites. So this is NMIC 1, NMIC 6, SES2, and Spaceway 3. And on the x-axis is the Mahalanobis distance, and on the y-axis is the fraction of the population. And as you can see, the blue line is the Johnson system, and the green line is the Sloan system. And you can see, for the most part, they lie right on top of one another, basically including all the population and showing that they cluster in about the same way. So there's really no major significant difference between the two systems. So in closing, I just want to say that we are very heartened by the fact that we think that we can go to the Sloan photometric system and maintain satellite discrimination capability while gaining, we hope, photometric accuracy. Thank you.
Any questions for Dr. Payne? We have time for a quick one.
So do you have any, you had mentioned something about the U-band and how like the detectors weren't sensitive to that, but do you have any data from other detectors where you might say, could it break some of the degeneracies that you had there for some of the telescopes?
Something about U-band, other systems, and then I couldn't hear the rest. Sorry.
Sorry. Do you have data from other systems, other telescopes that contain U-band data, which might say how useful it is?
I do not. I don't know if John do you know of any U-band data? Yeah. Sorry. No, I don't think we do. Maybe Jay, my colleague, can help me. No, he's shaking his head.
Sounds like the votes are in and it's a no. Okay, thanks very much, Mara. Our next speaker is Dr. Jiří Silha. Dr. Silha received his PhD in 2012 from Comenius University in Slovakia. He is presently a junior researcher at the Astronomical Institute of the University of Bern. His research interests include characterization and attitude determination of satellites from optical and SLR observations. The title of his presentation today is Comparison of ENVISAT'S Attitude Simulation and Real Optical and SLR Observations in order to refine the satellite attitude model. Please welcome Dr. Silha.
I will jump directly to the motivation. Just a second. So that you have the full picture, I would like to tell you that currently our institute, Astronomical Institute of University of Bern, is involved in ESA study. This study is dedicated to the attitude determination of spacecraft in upper stages, the compact targets which can be possible active debris removal missions in the future. The goal of the study is to improve different techniques, starting with photometry, going through SLR, which is satellite laser ranging, radar direct imaging, ISAR imaging, or radar cross-section. The reason why we would like to know the attitude of these big pieces is there are actually two reasons we are keeping in mind. One, as I mentioned, is the active debris removal. That means you would like to know, once you're approaching your target, how this target is behaving, or how it will behave once you go up there. And by behaving, I mean what is the spin rate of this target and what is the spin axis of your object. Second aim or second motivation is contingency scenarios. So what can happen is that you have a spacecraft on orbit, and suddenly you lose contact. And the first thing you do observation campaign using any asset you can imagine. For example, direct imaging from space or radar imaging from ground. First to identify if you have any damage. And the second kind of check is if there's something changed with your spacecraft. It means attitude. If it's tumbling, you want to see what was the angular momentum which was received by the spacecraft. Is it enough to be received from reaction wheels, or there was some kind of impact? If there was impact, what could be the size of the particle? What is the probability of such a hit? So this is the second motivation, which can help you somehow come up with a very quick, short time with a contingency, how to react to this contingency scenario. During the project, we are also developing a tool. The tool is called In-Orbit Tumbling Analysis Tool, IOTA. We call it shortly. And the main function of this tool is to predict the attitude in the future. First, short-term predictions. For example, you have observations from tonight, and would like to know how the objects are going to behave tomorrow. Secondly, long-term predictions. You're preparing your other mission, but you know it will take some time to get up there, 5-10 years. So you would like to know what to expect from your spacecraft in 10 years. So for that reason, we need these long-term predictions of the attitude. And last, not least, is the synthetic data generation. That means that you have your assumption of what's happening with your spacecraft. You feed this program, this tool, and it will generate for you, for specific paths, what kind of data you should get back. For example, for photometry, what kind of light curve or SLR ranges. So this is synthetic data generation is one of the functionalities. IOTA is still under development, and today I will just show you several tests we performed with this tool towards this direction. Most is focused on synthetic data generation. I will just add that IOTA will have implemented all possible torques you can imagine, gravitational, magnetic, air drag, solar radiation, but also you can simulate impulses, for example, simulating impact from a meteoroid or space debris piece. So to test IOTA, we need some good test case. One of the best investigated cases is ENVISAT. ENVISAT is a satellite which belonged to European Space Agency. We lost contact with it in 2012. And 1 month after the loss of contact and after many failed attempts to reconnect to the satellite, the mission was declared to be ended. And since then, ENVISAT is a space debris piece. Fortunately, the IRS network, which is the network of SLR stations, was continuing observing ENVISAT, because ENVISAT is equipped with the retroreflectors. Thanks to that, we are able to track it with very high precise orbits. When I'm mentioning ENVISAT is that this is actually good. It's a good case to test IOTA on, because there were several studies performed for it. Before that, I will also mention that it's a really big piece. It's 3 by 3 by 10 cubic meters, and it's more than 7 tons. So you can imagine if in case of fragmentation event, it will really contaminate the LEO region. ENVISAT is currently placed around 800 kilometers in a sun-synchronous orbit. In several years, several studies were dedicated to ENVISAT. For example, SLR, the altitude determination presented by Daniel Kucharski, he showed us that SLR can actually be used directly to determine the attitude state of the spacecraft. AIOB also dedicated research for the last 1.5 years towards this direction to use SLR, but we did a different approach. We used the SLR signal, the variation, the modulation, when you see actually how the retroreflector is moving to, or comparing to the center of mass. And we are trying to estimate parameters which are actually determining or describing the attitude of the object in the orbit. So this is our approach, and also it is important to mention that SLR is not the only way, because not all spacecraft, not upper stages, they are not equipped with retroreflectors. For that reason, we have to keep in mind that we have to have methods which are also dependent from SLR. For example, I will just point you to work from Koshkin and all from 2016, where the authors used specular reflection measured by video camera for ENVISAT, and from that they try to, or they determine the attitude state of ENVISAT. In a nutshell, all 3 studies actually show that ENVISAT is tumbling. It's currently decelerating. The tumbling rate was roughly 2 degrees per second in 2015, and we know that the spin axis is slightly tilted comparing to the orbital plane, normal to the orbital plane. So here, just for demonstration, this is during the active period of ENVISAT. You can see retroreflector is pointing towards nadir, is the purple thing, and this green line is actually indicating the SLR measurements. If you have active spacecraft pointing nadir, you will have nice flat signal from SLR ranges. However, in case your spacecraft is tumbling, what is happening is that So if the spacecraft is tumbling, the signal, you will see actually a modulation of the signal where the RRA is moving comparing to the center of mass. So we have our test case, we understand how it behaves, but now it's more important for us to require real data, which we can then compare to synthetic data we will generate with IOTA. Our major and most important equipment we have in our Zimmerwald Observatory is a 1-meter SIMLAT telescope, which is a combination of SLR station and optical system. And SIMLAT is able to do SLR, photometry, and astrometry. You can see this telescope on both panels. So in the end of August, we performed a short observation campaign where we focused on ENVISAT passes. We had in total 4 passes, 1 in 22nd, 2 in 25th, early and late pass, and 1 in 27th of August. You can see the geometry of the passes in topocentric system in the panels below. West is pointing down and north is pointing right. And except the early pass in 25th of August, all the passes were on west. The early pass was on the east. And these are the data we acquired. You can see, as I mentioned, on the upper panel, it's the SLR residua we measured. There are 2 types of information in it. Actually, one is the oscillation, which looks like sinusoidal behavior, and the other one is kind of trend, which goes, the whole signal is kind of tilted. I will elaborate on it on the next slide. So this is the pass from 22nd, and this is the later pass from 25th. The early pass, which was on east, we couldn't get any returns from SLR, but we could have a light curve, which I'm not showing here. So in the upper figure, as I said, you can see, again, sorry. You can see on this figure, this is the 3rd pass from 27th. And here you can see that except the sinusoidal behavior, we have this trend. And this trend is caused by the fact that our prediction and the real measurements the predictions are actually off a little bit. And this is actually the off estimation for the center of mass position. On the other side, the sinusoidal behavior is clearly caused by the RRA rotating around the center of mass. So we want to detach these two information and focus only on the attitude one, related to the attitude one. Below, you can see the light curve acquired by CMOS camera. We used 7.5 frames per second and 50 milliseconds exposure. And you can, if you compare these two signals, they were acquired simultaneously. You see that we have probably one rotation here. There are two minima. And we have roughly every 50 seconds one peak with light curve. So we have our real observations. And now it was necessary to fit IOTA to come up with some attitude, first estimation for the attitude, and try to figure it out actually how the object behaves. So first what we had to do is we have to put the object on the orbit. So we use TLE and SGP to simulate the geometry of the path. Then we needed to actually get some initial value for the inertia period, the tumbling period of the object. So for that, we use AIUB's internal procedures for SLR signal processing. And during this procedure, one of the side products is getting from apparent to inertia period by assuming some simplifications. So we determine the inertia period, or the value which we're going to use for simulation, to be 215 seconds. And we assume all the time two cases. One is the satellite is tumbling clockwise, and one is counterclockwise direction, comparing to the motion of the satellite on the orbit. So, for some physical parameters, we had to retrieve data from ESA or from IRS. For example, center of mass position, error rate comparing to center of mass, last known value, and moment of inertia of the spacecraft. And in the end, we have 3D model, which I already showed you. We constructed 3D model in IOTA, and we use it to generate the light curves, synthetic light curves. What was necessary more is do some more assumptions to simplify the whole problem. So for example, we know from reality, but also this will be one of the first assumptions you would do probably, that the spin axis, if there is any, is probably aligned with the principal axis of inertia. So we used this assumption, and what we did, we had to figure it out. Okay, we have all these settings. Now, what was the position, initial position of the spacecraft in space in the beginning of simulation, and what was the spin axis direction in the inertial system? This is the answer we wanted to answer. So this alignment in space we could describe by three angles, alpha, beta, gamma. And because we assume that the spin axis is actually aligned with the principal axis of inertia, this alpha, beta, gamma is not two sets of angles, but just one set of angles, alpha, beta, gamma. We don't need it for the spacecraft alignment and spin axis because they are aligned. So in the end, we run simulation. We go through a whole interval of alphas, betas, gammas from 0 to 360 or 0 to 180 degree, and we got and we generated SLR residuals, synthetic ones. These residuals will then compare to the pre-processed residuals we got in reality, and we were looking for the best match in the phase, in the amplitude, and so on. So in the end, we got two solutions for each pass, and we did only two passes, the best ones from the pass from, it's over here, from 22nd, and the later pass from 25th. For each pass, we had clockwise and counterclockwise solution. So on this plot, you can see solution, upper panel is counterclockwise and lower power is clockwise for the pass from 22nd. And this panel, or slide, you can see a light curve, which is the real one, is in the upper panel. And in the middle one is the light curve generated assuming counterclockwise case, and clockwise case is in the lower panel. I will jump for the other pass, which looks much nicer because it's much longer. It's almost 9 minutes of data. And here you can clearly see that we are in a very nice alignment between the blue and green line. Blue is the real data, and green line is the synthetic data we generated. And what is interesting comparing to the clockwise, that the upper panel, the apparent period is identical. The peaks stay aligned. This is not the case for clockwise, where we can see that there is a small shift, constant shift of the green line, which is the apparent period is larger than the small period, which is indicating that this kind of geometry is not favorable, but the right up one. The counterclockwise is probably the case. For light curve, we didn't have much conclusive result, but you can see that for real case, we have very nice peaks every 50 seconds. For the counterclockwise case, we have kind of distinguishing sharp peaks, but this is not the case for clockwise case anymore, where we have really big pieces of peaks, very wide peaks, which indicates that the whole geometry alignment was a little bit different than in reality. So I will summarize that we introduced you to the project we are currently working on. It should end soon. We are now still in the development phase. We will test IOTA. We are responsible for the photometry and also SLR. And together with our partners, we will try to develop it within the next 6 months. Maybe interesting information for you is that we have more data, not only these 4 passes of ENVISAT, and we have also simultaneous passes with Tyra radar, which did ISAR images along with radar cross-section. So we also use this data for comparison with the synthetic data. And we have more targets. It's not only ENVISAT, we have other 4 priority targets we will focus on and do testing for them and also come up with the attitude determination for these targets. And with this, I would like to thank you for your attention. And if you have any questions, please do not hesitate to ask.
Any questions? Yes, in the center.
I have a question, thanks. So you mentioned that you wanted to use this IOTA for helping with prediction, like long-term predictions of what something's doing. So I'm curious how you would use that method if you have, for example, if you determine that a satellite is not tumbling, how can you use those simulations to detect, say, in 5 years that it's going to be tumbling? Which is presumably what you want to find out.
No, that's exactly what happened. So what we've seen with ENVISAT was that it was stable right after the failure, a few months. And then suddenly there was acceleration. And what we want to do, for example, in this case, we want to simulate, OK, what kind of impact would cause such an acceleration? And if the object is stable, there's a good question. Should we expect anything to happen to it due to, for example, solar radiation? So if I put the spacecraft there, I will stop operating it. Are the stars going to spin up or not? So this long-term prediction should show you that. Welcome.
Very good. Thank you, Dr. Silla. Our next speaker is Tom Kellisey. Dr. Kellisey received his PhD in aerospace engineering from the University of Colorado Boulder in 1990. He is presently a senior scientist at Applied Defense Solutions. His research interests include algorithm development and exploitation for high-accuracy satellite metrics for object characterization and orbit determination. The title of his presentation today is Non-Imaging Characterization Assessment of Shedding Events from Derelict Satellites Near Geosynchronous Orbit. Please welcome Dr. Kellisey.
Thank you, Matt. Let's see, here it is. I should, well, thank you for sticking around. This last session's a tough gig. So I'm going to talk about ways you might be able to detect shedding events from satellites, and I should acknowledge my co-author Mark Skinner, not listed here, but deserving of acknowledgement is Doyle Hall and also Paul Kervin for the work they did. I leverage it heavily in here in this work. And then I'd like to thank Boeing for supporting the work and for my new employer, Applied Defense Solutions, for enabling me to be here to present it. So I'm going to skip this overview. So why do we care about shedding? Well, there's a lot of derelict satellites up there. Some of them are caught in a gravitational well, so they're oscillating, but the debris they shed sort of stays in that area, but some of it can get ejected. So one reason you might be interested is if you can trace a source of debris shedding, it might be a good candidate for debris, active debris removal, that particular object. There's some other reasons I cite in the paper, there are some active observing campaigns. Aerospace has been using their BAS sensor up on Haleakala to collect long-term measurements of some of these derelict objects. Also, Professor Francis Chun at the U.S. Air Force Academy has just recently started a program to use their sensors to do some long-term observing. So the questions that were motivated that motivated this work were, what sort of things should you look for if you're looking for evidence of shedding. And then a more difficult question to answer is how might you trace those back to a parent object. So I asked around several folks in the industry. I asked Darren McKnight if he had any good references for shedding, and he handed me a paper that dealt with microscopic type shedding events, chips of paint and so on. That wasn't really what I was looking for. I talked to J.C. Liu at NASA JSC. He didn't have any good references, and I actually also talked to Professor Thomas the Hammer Schildnick in the audience there, and he didn't have anything. So I had to do my own research. So happy autumn. Yesterday was the first day of autumn. So yeah, it happens in nature, right? So man's best friend sheds. That guy looks pretty sad. I think his owner's been in a conference all week. And ooh, yeah, that's a bad one. Cranial shedding. I should get Darren working on that. And to beat a dead shed, sheds shed nails, boards, and paint, and so on. So that's my argument. I'm going to tell you folks that shed happens. So I didn't have a lot of budget for this research. So these are some numbers of growing populations of derelict satellites. This is the western gravitational well, roughly in this area, and so these are some of the derelict satellites. Here's a list of some of the satellites that Francis's students are collecting data on, and this is just a simple analysis showing that if you were to shed a high area to mass ratio object from a derelict satellite, it would oscillate a little while, and then eventually the perturbation's enough for it to be ejected. So now it's out of the well and circling the geo belt. So just some compelling arguments. I'm going to skip over this because I'm going to talk about it in the analysis I did. So different ways you might be able to detect shedding. You have astrometric measurements that provides you positional information, and so if something were to shed, its mass properties are going to change, so that changes in its size, so that changes the orbital dynamics. And so what you see here on this, whoops, let's see, back up. So on this left-hand plot, this is the semi-major axis eccentricity and inclination of a solar panel, which has roughly 0.4 meters squared per kilogram, relative to its parent object from which it shed, a geosatellite. And you can see that over 50 years, it doesn't change very much initially, but then eventually does. In contrast, an MLI being shed, you should see that separation happening immediately. So the point to take away from this is that if you're going to have any chance of trying to trace something back, you have to follow up on it quickly or know that it's happening so you can start looking for the shed piece of debris. And even this is not a good, you can have, for example, MLI separating off a satellite. It's not going to change the mass properties or the size of the satellite it's shed from very much. So you're not going to see a perturbation in the host satellite. So, using astrometrics is not going to be a foolproof approach. And so how about photometry? So in this particular scenario, this left-hand plot is a pre-separation. I modeled a box-wing satellite tumbling, a derelict satellite near GEO. And so what happens then is I separated the solar panel, and so the mass properties change, and in this case we're looking at tens of minutes here, and so because the mass properties, the moment of inertia in particular change, that's going to change the dynamics, rotational dynamics. So if you're looking at, and I have two metrics here, one's albedo area product, and then this is visual magnitude. And you can see, you've seen these plots before. This was modeled with the BRDF. You can detect changes in rotation rate and possibly changes in effective area. But then again, some of this is dependent on how you're viewing the satellite, where you're viewing it from, and then after the dynamics change, it's going to change its mass moment of inertia property, so it's going to eventually migrate to some other steady state from what it was in. So this isn't a completely foolproof approach to detecting. And then to reinforce that, this is a simple-minded case where a nadir-pointing 3-axis stabilized satellite lost a piece of MLI, and you see no difference. So that just says that photometry has its limitations for being able to detect changes. So you heard John and Mara talking about spectral measurements. So you can get multi-band, multi-wavelength measurements on satellites to detect or to measure various material properties. So if, for example, you were able to take at different wavelengths over time optical cross sections and cycle through those, then you can perhaps have a way of detecting material properties. In this case, to exactly derive surface materials of unresolved objects, you have to have a wireframe model which models the size and attitude of a satellite in order to do this. And this is some work that's referenced in the paper that Hall and Kervin and others demonstrated. And so in this case, just to show that this is also a viable approach, I modeled a tumbling CubeSat, and the baseline had solar panels, solar cells on the plus minus X and Y surfaces, insulation on the top and the bottom. And the measurements were the multi-band, multi-wavelength type OCS measurements, and the model is a function of wavelength and aspect angle and so on. And so you compare that and do a least squares reduction. And there are actually two approaches. One can directly estimate the properties of the material properties of the surface, and another looks at a catalog of different materials. So this is my catalog axis here in this example, and this axis represents the surfaces. And so you can see that in this case, you fairly accurately recover the solar array and insulation surfaces. The only one you can't recover is this minus Z, because you don't see it. This color axis is the likelihood. So what happens if you lose a piece of material or two? So in this case, I went through, and you can read the paper, I went through several scenarios where I selectively lost a surface material, and in this case, there are two surfaces that are now changed. One is you've lost a solar cell, and now you have exposed aluminum, and then in this case, the insulation's gone on the plus Z axis, and you have steel exposed. And I should have mentioned, in all cases, I modeled the measurements over a 4 different days, 1 hour a day. And so you can see in this case too, you're able to recover, now you have aluminum exposed, and you still have your solar panels material for several of the surfaces, and you have one for steel. And so the idea here is, if you can get around that, use some of the existing techniques to characterize the size and the attitude behavior, you might be able to use these types of measurements. Now, something I've assumed here as well is that when you process a set of measurements, all those measurements contain just whatever those surfaces were when you process the measurements. But how do you really know that in the act of collecting your measurements that a change doesn't happen in the middle of those measurements? So what would happen there And so what I did was I looked at, I combined all the data that I simulated where you had the baseline configuration and then you lost the solar surface and now you have the other aluminum exposed, and so that data's in there, and then likewise the insulation. So what happens is you are now not able to unambiguously derive that something has shed from that CubeSat, but you do get still a good indicator of the, probably because it's still the dominant material. But so the good news here is even if you can't clearly identify the new material, you know, compared to the baseline, the original, and see that something's, you can't, even if you can't determine the exact material change that's occurred, you know something has changed between these if you've monitored previously, so, and established a baseline. So, so I think the real message here is there's no one measurement type or technique that enables you to unambiguously determine if something has shed from an object, but probably the way to go, in addition to persistent monitoring, and with all the sensors out there now, this becomes more viable. But the other thing to consider is that so you can, yeah, in addition to persistent monitoring, I think the combination of all of the different approaches, fusing the different information is probably the most reliable way if you have all those available on numerous objects, these derelicts, then you can combine those to put together a story. And that's all I have.
Questions for Tom?
Please don't make me ask a question.
Go ahead.
Given a lot of thought to the thermal cycling that occurs to a cantilever geostationary solar array after the satellite expires, because they're rotating about 500,000 or 1 million times a year. So thermally, they do deflect and then warm up on the side that's supposed to radiate heat during normal operation. So I was curious as to whether or not we should be looking for the failure mechanism in the long run of the life of a solar cell, because I'm curious if there's a lot of cover glass out there in geostationary orbit that we're never going to see.
Yeah, and maybe this addresses the question. In general, if you use LWIR, some type of thermal measurement of surfaces, you can, and if you're monitoring those persistently, then if something changes, you know, obviously a derelict satellite's going to go through some different thermal periodicities, you know, depending on season and so on, and eclipsing. But if you're able, that's just another measurement type you could use to monitor potentially shedding events. If you're looking at surfaces that absorb energy in a certain way and emit it in a certain way, and that material goes away, that's going to change the thermal properties, which you should be able to see. You know, Dave Whitty, I think he's gone now, but he could address that.
Thank you.
Thank you.
Thanks very much, Tom. Our next and penultimate speaker is Jay McMahon. Dr. McMahon received his PhD in aerospace engineering from the University of Colorado Boulder in 2011. He presently serves as an assistant research professor in aerospace engineering at the University of Colorado Boulder. His research interests include spacecraft GNC, astrodynamics, and small body science. And the title of his presentation today is Shape Estimation from Light Curves, including Constraints from Orbit Determination. Please welcome Dr. McMahon.
Thanks, Matt. So I'd like to point out that that's 2 buffs in a row, so that's good. We could get the streak going a little longer, I think, but there's a lot of us here now. So Today I'm going to talk about shape estimation from light curves using constraints from orbit determination. And I'm an astrodynamicist as opposed to an observer. And so I might have a little bit of a different angle here, but really what I'm interested in trying to figure out is I've done a lot of work with trying to understand how the attitude of something on orbit can influence the orbital state, right? So with solar radiation pressure or drag, for example. So here, we're kind of trying to do the opposite, where we want to use any information we can glean about the orbit and then see if that gives us extra information about the attitude or the shape. So basically here, I'm taking a high-level view and trying to figure out how we can do this process. And so the basic data set I'm working with is light curves, and that's kind of in quotes because I'm talking at a more theoretical level, I think, than a lot of people have at this conference. Light curves are often used to obtain attitude and shape information. The nice thing about light curves in lots of applications, if there's a periodic attitude motion, this sticks out in light curves, right? You see repeated brightness, and you can do FFT basically and lay things on top of one another. You can see that periodic motion. Of course, it gets harder when the attitude motion is not as stable or as periodic. You can tell that it's not a stable attitude motion, right? A simple spinning motion, but it's oftentimes hard to figure out what the actual attitude motion is. So in some instances, you can actually get shape information, but of course, I'll talk about this in a little more detail. It can take a lot of time to do that. You need a lot of measurements from a lot of different observing geometries for that to work out. So there's a few driving questions that I'm trying to get at with this research. So first of all, what is the shape information that we can get out of light curves? And as I'll talk about in a minute, it's not actually the shape, right? It's information about the shape, but we can't actually get the shape. So what are we getting there? And is there any way we can use this coupling between the orbit and the attitude to try and gain more information or gain information more rapidly? And finally, it would be really nice if we could do this without actually knowing the BRDF of the object you're looking at because, well, typically we don't know it. Okay, so a little background on shape estimation from light curves specifically. So there's been a lot of work and really nice work done in the asteroid community for coming up with non-convex shape representations of asteroids. You can see an example down there that I just pulled from the online database, damn it. And so this works great for asteroids because, first of all, it's quite likely that shape is not that far off from an asteroid shape. Many asteroids have this kind of top shape, look, and so this might not be that bad, right? It's not perfect, of course. It's not getting any convexity, but it could be close. And the other big thing that happens all the time with asteroids, and there's a lot of dynamical reasons behind this, is that oftentimes they're principal axis rotators, and their rotation axis is stable, like inertially fixed. So the light curves make it really easy to pick out. And you can see an example in the bottom right here. I pulled this from one of Petr Pravich's many papers on light curve analysis of asteroids. And you probably can't read the text. I don't know if I can make. Yeah, but this is data taken over a number of nights, right? But because the spin pole is fixed, you're able to lay them over one another, and you can quickly, of course, pick out the period that you see in this light curve. And finally, the last piece with this is that asteroids are diffuse reflective surfaces. So even though we don't know the BRDF exactly, you can say that it's basically a Lambertian reflector, maybe with a little more detail, and that's pretty good. But the problem is that this is not really true, right? We've known for a long time. Taft wrote a little technical note in 1978 that I found, and he lays out all the analytical reasoning for why you can't actually determine the shape from light curves, right? So you can determine a representation if you make some assumptions, like in the asteroid case, but you can't actually get the shape. It's impossible. Okay, so what can we get? right? That's not a real great way to start the talk, right? Like I'm tackling an impossible problem. So, but the question is, what can we get out of it, right? Obviously, we can get something useful, so let's look at that. So here's a little more detail on how light curve inversion typically works. For the asteroid case, Castellanen wrote kind of the seminal papers on this to come up with those convex hull shape models. And without going through the details here, you can find them in the paper. Basically, the BRDF is this combination of the Lamo, Seeliger, and Lambertian laws. It's hidden in the math over there. You assume a constant spin axis and period, right? So that's a big assumption that we don't always want to use for spacecraft. And of course, the shape representation is fixed. So you have this J index that's hanging out over here. That's the number of facets, and you're trying to estimate the area, right, of all of these facets. So you pick a shape representation. You say you have you start out with a sphere or something with 1,000 facets of equal area, and then you go from there. But you've already picked the fidelity of the shape. And of course, you can mess with that in between iterations, but you're fixing something that you don't actually know, right? So the way this actually works then is you get the light curves. You can pick out the spin state pretty easily, usually, well, for asteroids especially. And you basically you collect all the brightness measurements, which are on the left-hand side here. And then from all those brightness measurements, you can get these shape constraints, or in the asteroid case, you think of it as actually getting the shape. So what about when things get harder? Well, so I want to introduce this concept of a brightness map. There's probably another word for this that I didn't find in the literature, but basically what a brightness map is, what I'm calling it, is it's this map that you can think of as the BRDF of an object, but for the whole body, right? So BRDF is associated with some specific material, and it tells you the reflective properties that come off of it. In this case, we're using light curves, they're unresolved, we don't know the shape, so we can't say that the material properties of any specific part, we just get kind of this conglomeration of the whole object. And so if you have the brightness from any given observer and sun location with respect to the body, that would kind of give you all of the information you could get about the combination of shape and attitude of this body. So this is complicated because it's a map from a bispherical regime, right? So you have the position of the sun, the position of the observer in the body fixed frame, and it maps from those two domains onto just a real space of brightnesses, right? So this is a hard function to represent. And if you think about it, so this is saying basically you have 4 inputs to 1 output. If you think about it from an observer sense, you are typically thinking about it in an inertial frame, or maybe like the sun-Earth hill frame. And in that case, so you could say, okay, this got a little covered up, but this is the position of the sun right now, with respect to this inertial frame. And then let's just say, for easiness, that over the course of one night, the sun stays in one spot. Over the course of the observing arc, or really one orbit, I guess I could say, one arc. And then the observer position moves as the Earth rotates and so forth. And you get this light curve that you can map onto that space. The trick is, in this space, you haven't accounted for the attitude yet. So there's actually extra degrees of freedom here, and you don't get single values on this map. Okay, so you can get multiple values here. If you can resolve the attitude and move to the body fixed frame, so you express this brightness map in the body fixed frame, then your light curve doesn't necessarily make as nice of paths like you would intuitively think about. But the nice thing here is now you've resolved the attitude, so your brightnesses are single valued in this space. And if you have a single valued space, now you have this map, and you can try and represent that somehow in a way that you could estimate. So basically what you want to come up with is you want to come up with some functional form, and this is a severe sticking point for me right now, but you want to come up with this functional form that allows you to put in these 4 inputs and predict a brightness. Now if you were doing a forward model, you would also have to put in all of the shape and optical parameters of whatever you're trying to estimate. If you're seeing something on orbit and you don't know these, this is exactly why you can't get the shape out, because it's infinite dimensional. So if you can represent this functionally, you could use, if you had many, many brightness measurements or many light curves at different attitudes, you could use that to try and represent the shape in a way that you could then predict brightnesses at different attitudes. So the other side of this is you haven't said anything about orbits yet, right? This was supposed to be a talk about how to tie together attitude and orbit estimation. And so the idea here is that if you have a model for solar radiation pressure, you can use that information because it's correlated with the brightness measurements that you get out of the light curve. This gives you extra information to try and give you that brightness map. So this is the model that I've used in the past. I talked about this at AMOS last year and at many other conferences for those of you who have been around me, I guess. This is just an example of BRDF. But the point here is you can get a time-varying set of Fourier, or not time-varying, but geometry-varying set of Fourier coefficients to represent any arbitrary solar radiation pressure. So this is more complicated than the cannonball model. Right? So for example, here's just to show how the time variation, this can be represented with a set of Fourier coefficients, and I'll refer you this to the paper, and really this is from my paper last year, where we could show that theoretically you could actually start to estimate these Fourier coefficients to get the time-varying solar radiation pressure. If you have the time-varying, or I was just going to note, I saw a great talk earlier by Exoanalytics saying they were starting to see this, right, in some of their data. So this is really cool. So how can we use this, right? How can we use the SRP to help us with the shape or brightness estimation? Well, if you look at the math, you'll see that the kind of the mathematical form of the brightness, right, the light curve at any one time, that basically sits down here inside your SRP force, right? So this guy sits down in here. Of course, the SRP goes over all wavelengths, whereas your brightness might be over single wavelengths or some bandwidth. So it's not exact. It's not one-to-one per se. And in fact, the problem is if you had the brightnesses, you could, all brightness measurements from this brightness map, for example, you could predict SRP. You can't go the opposite way, right? So if you have SRP everywhere, you can't just predict brightness because you don't know all those relationships. But if you assume, and I hate assuming, but if we assume that the distribution of light, right, the distribution of brightnesses reflected over the surface of the spacecraft follows the same pattern as the SRP force, then if you have, for any given SRP force, this can give you constraints on the brightness over the entire shape, right? So if our observer is here measuring some light curve, and we have estimated the attitude of this so we know how it's moving around, so we get a measurement here, and we can say if the SRP is there, then basically the integral of all brightnesses over this region has to have a net brightness opposite of the SRP, right, which would be something over here. So basically what you can do is you can form a constraint on a set of brightnesses from your brightness map, and that has to be proportional and in the same direction as the SRP force. So this is the extra information you can get then to try and fill out the brightness map. So the process then becomes, before we had this process down here, this is your basic light curve inversion, which would give you shape constraints. The idea here now is if you've done this is really a high fidelity orbit determination, or at least high fidelity enough that you trust your SRP model, you can use that to give you a set of constraints and add those to your brightness map. So from a smaller set of light curve measurements, instead of having to actually fill out the whole brightness map purely with light curve estimate or measurements, you can augment that, fill out that map sooner, and that map is what gives you the information about both the shape and the attitude. So, final point, of course, this is not actually the shape, right? So I'm assuming that we've made progress, we've gotten the attitude, and we have this brightness map, right? But that is not shape. And the problem is, like I said earlier, you can't actually estimate the shape even if you had this brightness map perfectly. So hopefully we can fill out the brightness map more quickly with these SRP constraints added, but we still don't know things perfectly. So really the best you're going to do is through some sort of hypothesis testing. So you might have a catalog of objects, say, and you could say, this one matches or does not match the brightness map, this one doesn't match it, this one does. So it could be this guy, but we don't know for sure because of the infinite dimensionality issue. So I think I've spoken for long enough, so I'll leave this up, and if there are any questions, I would be happy to take them. And if anyone knows of a mapping I can use, please tell me. Thank you.
One very fast question, Dr. Vincent.
Since we know the truth now for Ceres and Vesta, I was wondering how the a priori estimates of what their shapes and reflectivities were from Dan's models, probably.
Well, I guess it depends on the resolution, right? Ceres was easy, that's a sphere, right? But Vesta is a little more complicated, but the a priori was pretty good from the light curves, yeah, for that one. Thank you for asking me a question about asteroids.
Thanks, Jay.
Thanks.
Our final speaker of this session and of our conference is Susan Haggerty. Ms. Haggerty received her MS degree in electrical engineering from the University of Colorado Boulder in 1987. She presently supports the Ball Aerospace and Technology Signal Processing and Modeling and Simulation Group. Her research interests include SSA, battlespace characterization, and missile warning. The title of her presentation today is A High-Fidelity Approach to Data Simulation for Space Situational Awareness Missions. Please welcome Ms. Haggerty.
Good afternoon, and thank you for sticking out here for the very last paper of the entire conference. I'm going to be talking about a high-fidelity approach to data simulation for SSA missions. I'd like to thank my co-author, Benton Ellis, who's done a lot of this work. On the left here, on your left, you see an example of our synthetic data. This is a sidereal rate example where, of course, the stars are stationary and we've appropriately streaked the RSOs. I've got a lot of slides here, so I'm going to go over them very quickly, some of them very quickly, including the agenda. Basically, I'm going to tell you why we think this is important, what we've been doing here, and then future steps and summary. So why do we think this is important? Well, we know that there's increasingly prevalent threats from foreign nations. And also, we've discussed quite a bit here in the conference that there's a large number of objects in space. These are both challenges that make it difficult to find new adversarial objects, detect changes, and identify bad behavior, all with a low false alarm rate. So these challenges, to solve these challenges, we need to develop enhanced SSA capabilities. And to do that, we need to evaluate and compare different mission architectures and optical system designs. We need to be able to test the efficacy of new algorithm approaches, and we need to be able to analyze and predict mission performance. And to support these tasks, Ball has developed an end-to-end EOIR simulation that provides realistic time-based mission and sensor data and corresponding truth. This slide is an overview of our modeling tool. We can model multiple observers. They can be either space-based or ground-based. They can be in various orbit regimes in space. Each frame, we propagate the positions of all the RSOs and the observers. We can support any kind of pointing and tracking that's desired. Two key examples are rate track and sidereal rate track. We feel that it's important to make sure that we're really detecting and discriminating objects and not just using like a simple SNR model to estimate if we're detecting these things. And so that's part of our motivation for adding a lot of high fidelity characteristics to our modeling capability. And a couple examples there in the list are, if you're, say, looking at the galactic plane, your star fields are very important to model, because if you have stars that are close to your RSOs, those could be challenging for detection and discrimination. Similarly, we model things like intraframe smear, intraframe jitter, and those can be reduce your signal noise ratio and hurt your detection capability. Also, environmental effects are very important, and we do include radiation hits and scattered light, as well as for ground sensors, atmospheric turbulence. This is the block diagram of our simulation tool. I don't have time to go over this in detail here, but it is in the paper. I'll just point out a couple key points. One thing we do is we create the motion blur kernel. And what we do there is we temporally oversample the pointing so that we can not only capture motions of the stars in the RSOs, but also additional high fidelity effects, like including the rotation and line of sight motion due to the gimbal motion, in other words, clocking. And another thing that's very important is we do the spatial oversampling so that we can get the correct spatial phasing from frame to frame, and we're not just using like average and squared energy. Okay, what are we using for target models? Well, we're leveraging a library of satellite models from the AFRL Satellite Assessment Center, and we use these to render radiometrically accurate images of the RSOs. And we render those at high resolution, and then we aggregate those back to the pixel size on the focal plane. And that's radiometric accuracy is conserved regardless of the angular extent of the RSO. And then in the bottom of the image here, just showing you some examples of the rendered images and what the modeled sensor would see as a function of the different ranges. And obviously, closer range, you get better resolution. We can also generate accurate light curves, and we do that by doing high-resolution rendering of the targets. So we generate high-resolution images at each point that we want to generate for the light curve, and then we aggregate all that energy into a single point for that point on the light curve. And here we're showing an example where we've done that for 2 passes for DMSP, observed from a ground station. And you can see, of course, you get different behavior, and we captured a significant glint on the second pass. And so this type of modeling is able to show you that glint behavior. And it could be used to support, for example, space object identification and characterization. We also have multiple ways that we can model the optical point spread function. We can use theoretical diffraction, of course, the Airy function. Sometimes we do close range modeling, and we want to occasionally include defocus, so we're able to model that as well. And then if we want to include say optical aberrations via Zernike coefficients, or atmospheric turbulence, and or the amplitude map for modeling, say, central obscurations, then we use a Fourier optics approach. And here you can see we have an example of in the pupil plane, an amplitude mask with the central obstruction in the support veins. And then that's the corresponding PSF using Fourier optics. We have 2 sensor models. We have an EO-IR sensor model, and then we have an active LiDAR model. And our EO model, EO sensor, of course, is sensitive to the visible and near IR wavelengths. We generate many characteristics, including the pixel-to-pixel fixed pattern noise, which, of course, is spatially fixed. But then to model the shot noise associated with that, we have random draws from a Poisson distribution. We add Gaussian random samples to model the read noise. We have a A to D model where we quantize the signal and convert it from electrons into digital numbers. And then we add many other additional high fidelity effects for detector artifacts. For example, in the right here, you'll see that we've modeled the CCD transfer smear, and we have actually seen that in some of our real sensors. And the fidelity in this approach leads to realism of the simulated data being close in spatial and temporal characteristics with real data. Okay, our other model is a flash LiDAR model. So for this model, we start with a radiometric image of the target. We oversample that spatially and temporally. We generate the LiDAR returns. We apply our imaging system effects, and then in our LiDAR detector model, and in this case, we add our noise sources and we aggregate to the typically lower resolution of the LiDAR sensor. I'm going to give you an example of that on the next page here. Here we have, on the left here, we have a time-integrated flash LiDAR return. So we've taken all the image planes based on the different ranges, and we've integrated the sum of all those. And on the right, I'm going to show you a movie in just a minute. But first, I'm just going to point out that you're going to see this near edge, and then there's going to be some blank time where there's no intersection with that part of the satellite, and then you'll see some of the other features of the satellite in the various image planes. So if you could start the movie, please. So you can see where you've got that near edge of the solar panel, and then you're going back in your image planes with over range, and then now you're starting to see the other image planes as they intersect with those range gates. Okay, we also model atmospheric turbulence. We do that using Rogman's approach. The resulting phase maps exhibit the von Karman power spectrum temporal and spatial coherence that we expect. We've done this for 6 combinations of layer weighting and Fried parameter for different observing sites and conditions around the world, including the Maui site. And I'm going to show you an example of that. In the middle here, we have an image of a Lambertian sphere without any atmospheric turbulence included. And then these are on the same scale. We have no atmospheric turbulence, and this will be showing you the images with atmospheric turbulence. And then this is the phase map over time, where you'll see the spatial incoherence. Go ahead and start it, please. You can see the spatial incoherence image correlation across the turbulence area. And then if you play the movie on the right, that'll show you the effect of that atmospheric turbulence on the Lambertian sphere image. Okay, we also include radiation hits. That's another characteristic that we need to think about when we're thinking about the front-end image processing for detection and discrimination. So we do that we have 2 angular distributions. We can do either isotropic or side-shielded radiation hit modeling. So if you play that movie, it's pretty short, so maybe just play it a couple times. You'll see that we're putting the radiation hits in our simulated data. That's good, thank you. Okay, so talk a little bit about future work and summary. We currently do articulation of solar panels for geo applications. We would like to add additional satellite component articulation, including for antennas and gimbals. And we'd like to do that potentially to support analysts for determining intent. What's the intent of that satellite? We'd also like to increase the fidelity of our stray light models. Stray light can be actually a really dominant effect and challenging for detection and discrimination. There's the new star catalog that was previously mentioned that is coming out next month, and we would like to be able to update our star catalogs to that newer, higher fidelity catalog. And we'd like to include additional focal plane artifacts, such as blinking pixels and additional bad pixel artifacts. In summary, we've developed a high fidelity EOIR active and passive simulation capability that enables advanced development of SSA architectures, payloads, and algorithms that's in support of key space missions and to address these current SSA challenges. This reduces program risk by following the test early and test often philosophy, and it also increases mission performance by supporting mission architecture studies. And that concludes my talk.
Yes, Dr. Payne.
Have you had a chance to test your results of your simulations with any real data to see how close you are?
Yes, that is on our list to do in the near future, but we have not yet done that. Good question. We have done some independent verification in terms of radiometry and things like that. But it's on our list to do that in the near future. Good question.
Yes, go ahead.
Another quick one. For the simulations you showed, it's mostly generating imagery. Would that then be passed into detection frameworks or what have you that are used for that system, or do you also incorporate running that imagery, getting into the proper format, and run through reduction algorithms?
This tool is part of it, can be integrated into a larger tool that we have called Mission X, and so it can be run closed loop or open loop as part of a larger simulation where we're doing all of the processing as well as generating the imagery. So you can either generate it kind of open loop offline with a GUI, or it can be, again, integrated into this larger simulation where you're doing the full end-to-end processing.